So welcome to Baltimore. This is where I grew up, and it's very exciting to see that Baltimore gets to host the joint math meetings, because that never happens. Happens all the time, but it's lovely to come home. My name is Ken Ono, and I was a member of the the MAA Invited Lecture Committee, and we had many outstanding nominations, and it's a great pleasure for me to introduce the next speaker, because I've known her for many, many years. Amanda Folsom, who will be giving this lecture, she's presently an associate professor at Amherst College, and she's led quite a distinguished career. After graduating from the University of Chicago, where I also happened to be a student, we loved it, she went to UCLA, where she wrote her PhD in analytic number theory with Bill Duke, who's one of the most distinguished analytic number theorists of our era. And I was very fortunate that after she completed her PhD, she chose to come to Wisconsin and work with us as a Van Vleck assistant professor. She enjoyed an NSF postdoc there, and it was a wonderful experience, I hope for Amanda, but it was certainly a wonderful experience for us in our group, because that's what postdocs do. They add a lot of life to your group, they enrich your research community, and that's, after all, one of the things that meetings such as this is all about. After her time in Wisconsin, she won a number of awards. She won an NSF Career Award. She's currently a Simons Fellow of some sort. She's been a member, I think, 2 times at the Institute for Advanced Study. Her first tenure track job was at Yale, where she was promoted to associate professor a few years ago. And for the last 4 or 5 years, I don't know exactly how many, she's been on the faculty at Amherst College. And there they are super lucky to have her. In any event, let me introduce Amanda. Amanda is going to give you a wonderful lecture, not entitled Emergency Exits. She's going to give you an overview on the genesis and the state of the art in a field called the theory of quantum modular forms. It's a very active field. And so help me introduce and welcome to the stage Amanda Folsom. Her lecture will be called Symmetry Almost.
Thank you, Ken, and thank you very much to the MAA and the joint meetings for the opportunity to speak. It's truly a pleasure to be here. So I'm going to talk about symmetry, or almost symmetry, guided by a certain mathematical story. And it's my hope that I tell this story to you in an accessible way, so that those of you who have not heard this story before can take something away. And I hope that for those of you who have heard this story before, or some parts of it, that you're hearing it in somewhat of a new way. So what is symmetry? Well, undoubtedly, this is a concept that we are all familiar with in many different capacities. So I'd like to start with a very short exercise and ask you to take 3 or 4 seconds and think about symmetry. What is the first thing that comes to your mind when you think of something symmetric? So I asked this same question to a number of friends and family members, colleagues, students, a number of months ago when I was thinking about this lecture. And as you can imagine, I received a number of different types of answers. So let's take a look at some of the answers that I received. So here are some examples of symmetry. I think we can all agree that the Taj Mahal, or some French garden, a vase, the Amherst College football field, these all exhibit symmetries. But how exactly are these things symmetric? These look like examples of symmetry in architecture, or locations, or with respect to objects. What exactly makes them symmetric? For this, I thought it would be interesting to take a look at what the dictionary has to say about symmetry. Does the dictionary truly capture what symmetry is? Well, I think all of the images on the previous slide agree with these first couple of definitions of symmetry in the dictionary. The first discusses a mutual relation of the parts of something in respect of magnitude and position. And the second talks about a harmony of parts with each other and the whole, a quality of being well proportioned or well balanced. So perhaps when I asked you to think of something symmetric a few moments ago, you came up with examples along these lines. Or perhaps many of you came up with very different types of examples. Let's take a look at a few more. So here are some more examples of symmetry. In my informal survey a number of months ago, butterfly and snowflake were the most popular answers. And perhaps some of you came up with examples along these lines. These are all examples of symmetry in nature. A flower, a crab, or maybe even the human face. These are all examples of natural symmetry. Is the human face actually symmetric? Maybe, maybe not, but somehow it's symmetric enough that we agree to call it or characterize it as being symmetric. So there's somehow a bit of openness in this definition of symmetry. And if we take a look at this sub-definition, this harmony of parts with one another can often be related to natural objects and structures, particularly the human or animal body. But then this definition goes on to say that this is associated to a regularity and beauty of form, fair or fine appearance. So somehow this part of the definition is relating natural symmetry with beauty. So there is some form of openness and a type of subjectivity involved in this aspect of the definition of symmetry. So all of these examples that I've mentioned so far exhibit a type of visual symmetry. But I think it's fair to say that symmetry does not necessarily need to be visual. It could be more abstract. And in fact, we can challenge the definition even further. Do we really equate natural symmetry with beauty? I scratched my head when thinking about this while writing this talk, and I quickly came up with some examples of natural symmetry that I did not find beautiful. Here's a spider, a moth. I find these fairly off-putting. Maybe you do too, or maybe you don't. Okay? Is symmetry really a rigid concept, or is it not? Here's a more abstract example of symmetry. Perhaps a harmonious relationship between people. Does symmetry only appeal to our eyes? Certainly not. Can symmetry appeal to other senses? Absolutely. Can we hear symmetry? Absolutely. There's a lot of symmetry in music. This is the score of a musical piece by Bach called the Musical Offering. This is an example of what's called a crab canon, meaning this piece sounds exactly the same if it's played forward or backwards. Whether or not you can read music, if I ask you to start at the top left of this score and you follow along the first few notes, that will look exactly the same as if we start at the bottom right, the end of the score, and move left. So this is a type of musical symmetry. And I certainly can't really go on much further in this talk without mentioning the following definition of symmetry that is more rigid in nature. It is more mathematical. This definition says that symmetry is an exact correspondence in position of the several points or parts of a figure or body with reference to a dividing line. More widely, a property by virtue of which something is effectively unchanged by a particular operation. So perhaps many of you, given that this is a largely mathematical audience, thought of examples of mathematical symmetries when I asked you to think about symmetry at the start of the talk. So let's take a look at some mathematical examples of symmetry. Here is a symmetric matrix, a bijection from a set to itself. Here is a symmetric polynomial, a fractal that exhibits infinite symmetries. And here's a simple graph that lives in 3 dimensions. So there are many examples of mathematical symmetries. And what I'd like to do to continue the mathematical story is to take a look at another graph. This next graph is not as simple as the graph of the function shown here on this slide. But if I show you the graph of this function, before I tell you anything about it, I think you can start to see the beautiful symmetries possessed by this function. The only thing I'll tell you right now about this function is that it's called the J function. And its graph is illustrated here with some very vibrant colors, and you can start to see symmetry properties exhibited by this function. So what is the J function? Well, the J function is often attributed to Felix Klein, circa the 1800s, when in reality it probably emerged before this time in the literature. This function plays many very important roles in number theory and mathematics. That's really a topic for a separate talk. I'm not going to tell you too much about this function, other than to offer this function as the type of function that exhibits the types of symmetries that I'll be discussing for the remainder of the talk. This function is defined on part of the complex plane. It's a complex function, and it's defined on the upper half of the complex plane, the part of the complex plane where the imaginary parts are positive. So to set your bearings, the axes we're looking at here are the horizontal real axis and the vertical positive imaginary axis. And the complex number I is just about at the center of this graph. And what we're looking at here are the complex values taken on by the J function on this upper half plane. These complex values are indicated by color. So how does this work? Well, we can realize a complex number via an argument or an angle and a magnitude or absolute value. So the idea is to use a different color to represent the argument of such a complex value, and then to use a darkness or lightness of that color to indicate the absolute value, how small or large it is. So again, just to set your bearings, if we take a look at the middle of this graph, where I is located, we see a red color. So that should indicate that the value of the J function at I is some positive real number, according to this key. And that's true. J of I is 1728. If you move a little bit to the left, you see a type of black hole. And this black hole is supposed to indicate that the value of J at the complex root of unity e to the 2 pi I over 3 is 0. So you can start to see the beautiful symmetries possessed by this function. How exactly is it symmetric? J is symmetric with respect to the following tiling of the upper half plane. So here's the same upper half plane, or portion of it, that I showed you on the previous slide. And it's sliced up into many pieces. In fact, this is supposed to represent infinitely many pieces. And if you see these pieces, some of them look like rectangles. These are supposed to be infinitely tall rectangles with circular bottoms. And some of them look like curved triangles of sorts. And some look like they get infinitely small as we approach the real axis. This is a kind of tiling of the upper half plane. And before I get too technical in explaining what this tiling is and how J is symmetric with respect to it, I want to explain this tiling by way of an analogy. The analogy I'd like to give is that of a jigsaw puzzle. I'd like you to think of this tiling of the upper half plane as something like a jigsaw puzzle with an infinite number of pieces. I've shaded one of these pieces in gray. And imagine that this jigsaw puzzle possesses some very special properties. So this one puzzle piece is very special in the following sense. I'm going to flip that puzzle piece over, and what are you looking at? It looks like you're looking at an eye, maybe an eyebrow living above this eye. Okay? So the very special property attached to this infinite jigsaw puzzle is as follows. It is enough to have in hand this one puzzle piece in order to understand what this completed jigsaw puzzle will reveal a picture of. What are we looking at here? When we put this puzzle back together, are we looking at a picture of a person? Are both of its eyes open? Is one closed? Are we looking at multiple people? Is there an animal? What's happening? Just having this one puzzle piece in hand is enough. And moreover, this puzzle piece will tell you how to put the completed puzzle back together. This is a very special property. So what are we looking at? A cat. So back to the J function and this tiling of the upper half plane. You can think of this gray shaded region as something like one of these special jigsaw puzzle pieces. The idea is as follows. It's enough to know the values of the J function on this very special puzzle piece. We call it a fundamental domain. In fact, it's enough to know the values of the J function on any single puzzle piece, whether it's the one I've shaded or any other piece. Well, let me tell you a little bit about what's under the hood. What is the mathematics behind the scenes? There's a group action at work. I will let gamma stand for the modular group. This is a set of matrices, 2 by 2 matrices with integer entries and determinant 1. This group is generated by the matrices T and S, where T is the matrix 1, 1, 0, 1, and S is the matrix 0, minus 1, 1, 0. And this group defines an action on the upper half plane, a kind of multiplication, as follows. If we take a matrix A, B, C, D in the modular group, it acts on a point tau in the upper half plane by sending it to another point A tau plus B over C tau plus D. A short exercise will reveal that this is indeed another point in the upper half plane. So if we think about these generators, T and S, T takes tau to tau plus 1. The complex number tau is moved 1 unit to the right. And S takes tau to minus 1 over tau. And the point is that J is symmetric with respect to this group action of the modular group on the upper half plane. Meaning, for any point tau in the upper half plane, J of tau plus 1 is the same as J of tau. For any tau in the upper half plane, J at minus 1 over tau is the same as J of tau. For any matrix A, B, C, and D in the modular group, J at A tau plus B over C tau plus D is the same as J of tau. It's in this sense that the J function is symmetric. Well, if you've been paying close attention, you'll realize that my analogy to this jigsaw puzzle, which revealed a picture of a cat, is not quite perfect. But I think you get the idea. And if you'd like to see what is happening with respect to the tiling, here is our fundamental domain, our very important jigsaw puzzle piece, shaded in gray. One of these generators of the modular group takes that region and moves it 1 unit to the right, the matrix T. The matrix S sends that region, as indicated in the image, to this triangular type region underneath, and so on. In this sense, the upper half plane is tiled. Okay. So, more broadly, these types of symmetries are the types of symmetries that functions called modular forms possess. J is an example of a modular form. Okay. How do we write these functions down? Well, they're not as simple to write down explicitly as, for example, that graph that lived in 3 dimensions that I showed you towards the beginning of the talk, but they do have explicit power series expansions. And these power series expansions are written down in the variable Q. This is the standard modular variable. And if you remember that the variable in the upper half plane, I've used the variable tau. Secretly, this parameter Q depends on tau as follows. Q is equal to e to the 2 pi I tau, and we'll suppress the dependence on tau in order for the notation to look a little simpler. So here is the Q expansion, at least the first few terms in the Q expansion for the J function. J is 1 over Q plus 744 plus 196,884Q, and so on. This is an infinite series expansion in the variable Q. Okay. Well, let's take a look at another modular form. This is the Dedekind eta function. So here it is, named after Dedekind, and I've written down again the first few terms in the Q expansion for the eta function. I think this is arguably a bit more predictable than the Q expansion that I wrote down on the previous slide for the J function. And I've also showed you here the graph of this modular form eta. Perhaps it's a little bit more difficult to believe based on this graph that the eta function truly is modular in a similar way to the J function, but it is. Okay. So depending on what you're interested in studying, it may be enough for you to work with the Q expansion of a modular form. It may be enough for you to stare at one of these colorful symmetric graphs, and that may not be enough. Okay? It may be more convenient to repackage your function in another way. We do this all the time in math. If you're trying to study something, it may be very helpful to rewrite it in order to truly illuminate its properties. So there's a beautiful way to repackage and rewrite this Dedekind eta function. It possesses a very beautiful infinite product expansion. And here it is. So I've slightly normalized. I've divided by Q to the 1 over 24 just to make the right-hand side look even cleaner. So this slightly normalized eta function can be written as the infinite product 1 minus Q times 1 minus Q squared times 1 minus Q cubed, and so on. Again, under the change of variable, Q is e to the 2 pi I tau. So this is a beautiful way to repackage the eta function. I'd like to mention another type of repackaging that we can sometimes attach to modular forms. And this example will be with respect to 1 over the eta function. So I just showed you that eta can be written as an infinite product. Therefore, 1 over eta can be written as 1 over that infinite product. But I'm not going to show that type of repackaging to you. I'm going to show you another type of repackaging as what's called a Q hypergeometric series. So here it is, 1 over eta up to normalization by this Q to the 1 over 24 can be written as follows. So if you stare at this for a few moments, I think you can figure out the pattern. This is to indicate an infinite series. You see in the numerators of each term some square integer power of Q, and you see in the denominators some very predictable binomial terms. We see the square of 1 minus Q in the second term's denominator. We see the square of 1 minus Q times 1 minus Q squared in the third term's denominator, and so on. These types of functions where we see these types of binomial terms are referred to as Q hypergeometric series. But let's get back to symmetry. We've taken a slight detour in thinking about some of the technical aspects of modular forms. Let's go back to this question of symmetry. And I want to think about perturbing symmetry. What types of perturbations can you make to something symmetric that will keep that something symmetric? Well, that definitely depends on what you have in hand and what types of perturbations you make. So if I take this very symmetric butterfly and I carefully change the size and shapes of part of its wings, well, I'm left with a butterfly that is still symmetric. If I change the color of this butterfly, it remains symmetric. But I can also make some changes that really destroy the symmetry properties of this butterfly. If you look closely at the butterfly on the bottom right of the slide, you'll see that I have changed the size and shape of one of its wings, as well as the pattern. So there are certainly things that can be done to destroy symmetry. So let's take a look at this Q hypergeometric expansion for 1 over eta. Well, eta is symmetric in the sense I described earlier. 1 over eta is also symmetric. I'd like to make a very subtle change to this function. I'm going to take all of the minus signs that appear in the denominators and turn them into plus signs. And my question is this perturbed function still symmetric? Well, maybe your first question is, why on earth would I be looking at this perturbed version of the Q hypergeometric expansion for 1 over eta? The answer is because this function appeared in the literature about 100 years ago. And here it is, as it was originally written down almost 100 years ago. Back then, and still today, this function is called f of q. This is an example of what's called a Mach theta function. This function appeared with a couple handfuls of similar Q hypergeometric functions in a letter that the Indian mathematician Ramanujan wrote to his mentor Hardy in 1920. And here in red, I've circled the Mach theta function f as it appeared on a page of Ramanujan's letter to Hardy. And what I'm going to do next is read to you exactly what Ramanujan said about this curious Mach theta function in his letter to Hardy. And then we'll spend a few minutes unpacking what he was talking about. So he says, I have proved that if f of q is the function that I defined on the previous slide, then f of q plus a very explicit function in q that I'm not going to read out loud for you at the moment, but there it is on the slide, f of q plus some very explicit function is bounded at all the points such that q is minus 1, q cubed is minus 1, q to the 5th is minus 1, q to the 7th is minus 1, and so on. And at the same time, f of q minus that same very explicit function in q is bounded at all the points such that q squared is minus 1, q to the 4th is minus 1, q to the 6th is minus 1, and so on. So what's happening? Why is Ramanujan studying this perturbed version of the Q hypergeometric expansion for 1 over eta at these points such that q to the n equals minus 1? He's studying the function at its singularities. So take a look at this function. As defined, you can just see from definition that it has singularities when q is minus 1. It also has singularities when q squared is minus 1, or when q equals plus or minus I. It also has singularities when q cubed is minus 1, which means q is minus 1, or the complex roots of unity e to the pi I over 3, or e to the 5 pi I over 3, and so on. This function has singularities whenever q to the n equals minus 1 for any positive integer n. So Ramanujan is studying this function at its singularities. Where do these singularities live? They live on the boundary of the unit disk on the unit circle. So here are these roots of unity singularities. Minus 1, that's referred to as a second order root of unity because when raised to the second power, we recover 1. E to the pi I over 3 is a sixth order root of unity because when raised to the 6th, we recover 1. And you'll notice in this picture that I've drawn some arrows. Ramanujan is studying this function f of q asymptotically as q heads towards these root of unity singularities radially from within the unit disk as shown. What I'm going to do next is paraphrase in a bit more detail what Ramanujan is getting at. He says that there's some explicit symmetric modular form, a truly symmetric modular form in the sense that I mentioned earlier, that cuts out these exponential singularities of the Mach theta function f. Meaning, as Q radially heads towards any even order 2k root of unity singularity of this Mach theta function f from within the unit disk, then f plus or minus that symmetric modular form is bounded, it's big O of 1. Meaning, asymptotically, towards these singularities, this Mach theta function looks almost symmetric. It's close to a modular form in the sense that the Mach theta function plus the symmetric modular form or minus the modular form is bounded. There's an almost symmetry here. Well, if we remember that in the language of modular forms, we like to think of Q as being equal to e to the 2 pi I tau, what Ramanujan is doing is the following. He's looking at tau vertically heading down towards a rational number on the boundary of the upper half plane. Under the mapping tau goes to Q, e to the 2 pi I tau. This upper half plane is mapped to the unit disk. The boundary of the upper half plane, the real line, is mapped to the boundary of the disk, the circle. And these rational points are mapped to these roots of unity singularities. So he's looking at a type of boundary behavior. So asymptotically, these Mach theta functions appeared to behave like symmetric modular forms. Volumes of literature were produced surrounding these Mach theta functions. But despite that, it remained a fundamental question to truly understand exactly how these Mach theta functions fit into the theory of these symmetric modular forms. In 1935, Watson, who was then president of the London Math Society, summarizes this in the following quote. He says, "The pages in which Ramanujan explained what he meant by a Mach theta function are very obscure." Ramanujan also passed away in 1920, so it was impossible at this time to go back to Ramanujan himself for more information. If we fast forward even further to 1987, Freeman Dyson stated at a centenary conference on the 100th anniversary of Ramanujan's birth that this remains a challenge for the future. Well, in some sense, the future is here, and I wanted to show you some graphs. Using the same way we graph the J function and the eta function, here's a graph of the Mach theta function f. Do you believe this Mach theta function f is or is not symmetric based on this graph? Well, for comparison, here is a graph of the modular form b, this function that seems to cut out these exponential root of unity singularities. This function truly is symmetric. Can you believe either of these things from the graphs? Maybe, maybe not. Well, it's now 2019, and I can tell you the punchline. So here on this slide, I've decorated the slide with a few other of Ramanujan's Mach theta functions. There were 17 original Mach theta functions, again, all Q hypergeometric in nature. You'll see the f of q function we've been studying at the top of the slide, and you'll see another function called f of q at the bottom of the slide. This is a different f of q that Ramanujan wrote down using the same notation. You'll also see two functions called psi, which are different. Well, the punchline is that these Mach theta functions exhibit modular symmetry almost. And what I'd like to do for my remaining time is explain two different yet very interrelated ways in which these Mach theta functions exhibit modular symmetry almost. Well, the first answer comes from some very groundbreaking work of Sanders-Zwegers. This work comes from circa 2002. It's relatively new, and it is due to Sanders-Zwegers. At the time, he was a PhD student under the direction of Don Zagier. And I'll paraphrase his work in the following statement. Zwegers proved that Ramanujan's Mach theta functions are not themselves symmetric. They're not modular, but they can be completed. And I'll explain what that means in a few moments. They can be completed to form certain symmetric modular forms. So some kind of construction must be done. Let me explain this by analogy first before we get technical. So here is this non-symmetric butterfly. I still find this non-symmetric butterfly to be quite beautiful. Okay? And what Zwegers has done is analogous to the following. Turning this non-symmetric but very beautiful butterfly into a truly symmetric creature that is a bit off-putting, in my opinion. So some not quite symmetric function that is aesthetically pleasing can be turned into a truly symmetric creature that perhaps is not as pleasing to look at. Let's do some construction according to Zwegers' work. How do we see this with respect to this Mach theta function f? First, it needs to be multiplied by q to the minus 1 over 24. That's not enough. This remaining function is not symmetric still. But the beauty of Zwegers' work is as follows. He shows that we can add another function that I'm denoting by f minus of q. We can add another function to this slightly normalized Mach theta function f to produce something that is symmetric, but there's a caveat. This function that Zwegers adds is not holomorphic. It doesn't possess suitable differentiability properties. It doesn't have a very nice looking Q expansion as we have for the Mach theta function f. Well, let's give a name to this sum. I'll call it f hat of tau, where Q is e to the 2 pi I tau as usual. This completion of the Mach theta function f is truly symmetric up to this caveat that the portion we have added is no longer holomorphic. Okay. So what's under the hood? What exactly is going on here? Here is this non-symmetric, beautiful Mach theta function f. It has a beautiful Q expansion. By Zwegers' work, this function is turned into the following truly symmetric function up to the expense of this not holomorphic function that's on the bottom right of the slide. This is some kind of complex integral. This is the function f minus of q that I wrote down on the previous slide. It's a type of complex integral that we typically refer to as a period integral. Okay. Well, it turns out that around the same time Zwegers was working out these results, the overarching theory of harmonic mass forms was being developed. Harmonic mass forms were originally defined in the literature by Jan Brunier and Jens Funke. They have similar definitions to ordinary mass forms that appeared in the mid-20th century. And in general, these harmonic mass forms have components that, like the Mach theta functions, are not quite symmetric, but are holomorphic. And when completed, they are truly symmetric, but they are not holomorphic. So this theory of harmonic mass forms has been developed over the last approximately 15 years. It's still being developed today by a number of authors, including Katrin Bringmann, Jan Brunier, as I already mentioned, Bill Duke, Jens Funke, Ken Ono, Don Zagier, Sanders-Zwegers, and others. So there is an overarching theory surrounding just how these Mach theta functions are almost symmetric. So this is a beautiful answer. But I'm not going to stop my talk here. I want to continue and think about this asymptotic closeness that we saw earlier in the talk. How are these Mach theta functions almost symmetric in this regard? Well, remember Ramanujan said that there's some explicit symmetric function that cuts out the exponential singularities of f. Okay. He said a bit more in his letter to Hardy, but not too much more. Okay. He didn't write down complete details or complete proofs. If we recall the quote of Watson, what Ramanujan exactly meant by a Mach theta function was rather obscure. So I'd like to play for you a short clip from the 2015 film, The Man Who Knew Infinity. This film was made about Ramanujan, and what I'm going to show you is a short dialogue between Ramanujan, played by Dev Patel, and his mentor, Hardy, played by Jeremy Irons, that I think characterizes the situation well.
How did you know that theorem?
It came to me. Mr. Hardy, I don't understand why we waste our time doing all these proofs. I have the formulas.
It's not that I can't see what you've claimed. It's that I'm not sure that you know how you got there. Or indeed that your claims are correct. There are subtleties which...
But they are right, sir. I have more important new ideas.
Yes, but intuition is not enough. It has to be held accountable.
Okay. So with that, and armed with the overarching theory of harmonic Moss forms, Ken Ono, Rob Rhodes, and I went back to revisit Ramanujan's observations. And the first thing we did was take a look at what was happening computationally. And for that, we have to thank Robert Lemke Oliver, who performed these very delicate calculations for us. The first thing we did was try to take a look at what was happening as Q radially approached the very simple second order root of unity minus 1. And as expected, the Mach theta function f appears to blow up. More interestingly, according to Ramanujan's observation, if we add this truly symmetric function b to f, it looked like this sum indeed was bounded, and it looked like that this radial limit was approaching the number 4. We performed a similar calculation approaching the root of unity I radially from within the unit disk. And in this case, according to Ramanujan's observation, f of q minus the symmetric modular form b should remain bounded, and indeed it looked like this radial limit difference was approaching 4i. So at this point, a naive conjecture might be that if one radially approaches some root of unity singularity of the Mach theta function f, then f plus or minus this symmetric modular form b should be plus or minus 4 times the root of unity you're approaching. Checked out in the first two examples. Okay. We set out, again, now armed with more of this overarching theory of harmonic Moss forms. What are these implied constants? And where do they come from? Well, it turns out that the radial limit sum or difference is not as simple as plus or minus 4 times a root of unity zeta that one is approaching. It turns out that we found an expression for these constants as polynomials in the roots of unity being approached. So technically that does answer the question, what are these implied constants, but it certainly doesn't explain where they come from. Perhaps these are very peculiar looking polynomials. Well, for that, let's think about what we know and what Ramanujan was looking at. We now know, thanks to work of Zweigers and the overarching theory of harmonic Moss forms, that these Mach theta functions possess an almost type of symmetry in the upper half plane. And Ramanujan is looking at what happens as we head down to the boundary of that upper half plane, as we look at what's happening at rationals. So is there some kind of almost symmetry or symmetry along this boundary? And this is where the relatively recent work of Don Zagier comes into play. Quantum modular forms. I'm going to read a quote from Zagier's paper titled Quantum Modular Forms that seems to fit the setting. He says, we want to discuss another type of modular object which we call quantum modular forms. These are objects which live at the boundary of the space, are defined only asymptotically, and have a transformation behavior of a quite different type. This sounds a lot like what we're looking at here with respect to Ramanujan's observations. A little more technically, quantum modular forms are defined in Q, the set of rationals, and they take values in the complex plane. And on Q, they exhibit modular symmetries, almost. Almost how? Up to the addition of some smooth error function in the real line. So let me show you a picture to make a little more sense of quantum modular forms. The following pictures come from Zagier's original paper. So here's a graph. Remember that quantum modular forms are defined in Q, the set of rationals, and they take values in C. This graph here is a graph of just the real part of a quantum modular form. The graph of the imaginary part looks quite similar. And what you're looking at looks like a lot of points scattered all around. This looks like a bit of a mess. But the idea behind Zagier's quantum modular forms is that there is a way to smooth out this function. And the way you do that is precisely by looking at the errors to modularity possessed by these quantum modular forms. So here's another picture from Zagier's paper. And on this graph, you see two curves that look quite smooth. One of these is the real part of the error to symmetry of this quantum modular form, and the other is the imaginary part. What do I mean by error to symmetry? This is showing something like the real and imaginary parts of the following difference. G of x minus G of minus 1 over x. Remember, minus 1 over x is attached to one of these generators of the modular group. If this function g were truly modular on Q, then you would want this difference to equal 0. But it's not 0, and it's not supposed to be according to Zagier's definition. It's supposed to extend to some smooth function in R, and that's what we're looking at in this picture. Now, if you really carefully look at this graph, you see that something funny is going on at -1/2. There is a singularity for this particular quantum modular form at -1/2. You can look at Zagier's original paper for those precise details. But more or less, what we're looking at is the type of error captured by g of x minus g of minus 1 over x. So the way in which these quantum modular forms fail to be analytic is precisely offset by the way in which they fail to be modular, and vice versa. So back to Ramanujan. Here is this funny polynomial. It turns out that this funny polynomial can be realized as the value of a function defined on Q. That's not too difficult to believe, but beautifully, this function can be realized as a quantum modular form. How do we see that? Well, let's take this funny polynomial in the root of unity zeta and turn this into an infinite sum. Step 2, I'm going to take away this symbol for the root of unity zeta and replace it by e to the 2 pi I x, where x is some rational number. After all, that's how we write down roots of unity. And I'm going to give a name to this function. I'll call it u of x. And a beautiful theorem due to Bryson, Ono, Pittman, and Rhodes is that this function is a quantum modular form in the sense just defined by Donzagier. If you think about this function a little bit further, what happens when you plug in some rational number? When you plug in a rational number for x, this infinite sum becomes finite. In terms of this observation of Ramanujan, we see on the right-hand side of this radial limit the value of this quantum modular form at some rational number. So what do we have here? We have in one single asymptotic statement a closeness between a Mach theta function, a Mach modular form, a truly modular form, and a quantum modular form. A function that's almost symmetric in the upper half plane is related to a function that is truly symmetric in the upper half plane by this radial limit in the sense that we recover the special value of a function that is almost symmetric in the rationals. And again, if we remember that quantum modular forms, Mach modular forms, harmonic Mass forms, these are all relatively new subjects, largely studied within the last 15 years or so. So I think it's safe to say that in this sense, Ramanujan was a bit ahead of his time. So the story certainly doesn't end here. We now have generalizations and extensions of the same story to all other Mach theta functions of Ramanujan. We have extensions of this story to what are called universal Mach theta functions, more generally speaking. And we now have the same picture attached to these holomorphic parts of harmonic Mass forms more generally. And for this, I encourage you to take a look at beautiful work by authors including Griffin, Ono, Rowland, Bringman, Choi, Lim, Rhodes, Zhang, Lobrick, and others. More generally, thinking about the theory of harmonic Mass forms and quantum modular forms, we have many applications outside of number theory to other areas such as mathematical physics, moonshine and representation theory, combinatorics, topology. Katrin Bringman, Ken Ono, Larry Rowland, and I recently co-authored a book on the subject. Here's the first page of our bibliography. At the end of this book, there are about 20 pages of references. So I encourage you to search the literature for a number of further results along these lines. Tomorrow, there is a MAA invited paper session that you may wish to attend at 1 o'clock, where you can hear more about some of these topics. And with that, I'll close. I hope that you have enjoyed thinking about symmetry and almost symmetry. Thank you.